Bismillah. So let's start with the first lecture. Of the EE 740, which is the advanced analysis of electrical machines. And simply we'll start with something we call the basic principles of electrical machine analysis. Now, in general, you know that any electrical machine consists of three parts. So simply, let's assume that I'm having three blocks here that represents the main component of the electrical machine, or the main ports of the electrical machine. So any electrical machine must have what? In general, any electrical machine must have electrical system, mechanical system, and what else I should have? So simply here, I must have electrical system, or sometimes we call it electrical port. And here we should have a mechanical system, or sometimes we call it mechanical port. And we must have a medium in order to transfer the energy between the electrical system and the mechanical system. If we are interested in the motor action, or from the mechanical system to the electrical system, if our concern is the generator action. So simply here, I need a medium in order to let's say transfer the energy between the electrical system and the mechanical system, and this actually what we call the coupling field. So simply here we have a coupling field.
دكتور نقدر نحكي عن الشافت؟
No. So simply it's not a shaft. The coupling field is the main component of the electrical machine and transformer. Without it, I cannot, let's say, transfer energy between the mechanical system and the electrical system. And you know that in general, either in the electrical system or in the, let's say, electrical machines or in the transformer, the electrical system and the mechanical system are not directly linked to each other. They are magnetically linked to each other. This is not the structure of the machine, which consists of stator and rotor, and in the rotor I'm having here shaft. Here the shaft, where I will connect, let's say, the mechanical system, and here where I impose the electrical system, either in the stator or if I need excitation in the field. So simply, this can be replotted as a simple block which has three parts. One is the electrical part, and the second one is the mechanical part, and also we have the field part. So simply this is the electrical part This is the mechanical. Port, and this is the field, let's say port. And how I can link, simply this will be the magnetic field. So if the energy is transferred from the electrical to the mechanical, this is actually called motor action. And if the energy is transferred from the mechanical port to the electrical port, this is actually called the generator action. And simply here, in this chapter, let's say, we will study the magnetically coupled circuit and the theory of the electromechanical energy conversion. So simply, in this chapter or lecture, let's say, according to the time, we will study the magnetically coupled circuit, and the theory of electromechanical energy conversion. Now, why we are interested in the magnetic coupled circuit and the theory of the electromechanical energy conversion? Anyone can answer this one? Why we are interested in the magnetic coupled circuit?
دكتور because يعني هي الميكانيزم للعمل الآلة.
Yeah, which means that the magneticable circuit is the central of the operation of the transformers and the electrical machine, correct?
Yeah. Right.
So simply here we can write that the magnetically coupled circuit central to the operation of transformers and electric machine. So, for example, in the transformer, we have stationary circuit. In the transformer, simply the circuit are stationary, which means that there is no moving part. So simply here, stationary circuit are coupled together in order to change the level of the voltage and the current. So stationary circuits are magnetically coupled in order to change the level of the voltage and the current. While in the electrical machine, we have circuits in relative motion. So simply here we have circuit in relative motion are magnetically coupled in order to transfer energy between the electrical and mechanical system. So circuits in relative motion are magnetically coupled in order to transfer energy between electrical and mechanical system. Yeah, that's why we are, let's say, interested in the magnetically coupled circuit, because they are the core of the operation of the transformer. In the transformer, in general, I don't have any relative motion. The machine, actually, the transformer can be called as a machine. Yeah, but simply here, all the circuit are stationary. There is no motion in the primary or the secondary of the transformer. And simply we need the magnetic circuit in order to couple the stationary circuit in order to change the levels of the voltage and the current. And this is the idea behind the transformer, is to shape the levels of the voltage and the current while not changing the frequency, for sure. For the electrical machine, in general, I'm having stator and the rotor, or I'm having, let's say, a mover, which is the rotating part or the moving part, and those, each of them, let's say, has a circuit, and those circuits are in relative motion, which coupled together in order to transfer the energy between the electrical and the mechanical system. If the energy is transferred from the electrical port to the mechanical port, then in this case, this is the motor action. And if the energy transferred from the mechanical port to the electrical port, this is the generator action. This is actually the magnetic coupled circuit. And later on, we will define how we can drive the mathematical model of the magnetically coupled circuit. What about the theory of the electromechanical energy conversion? So simply until here, we are highlighted, let's say, the importance of the magnetically coupled circuit. And now we need also to understand why we need, or the meaning of the electromechanical energy conversion, the theory of the electromechanical energy conversion. Now, simply, if I'm raising a question here, if I need to model this system, then in general, I will write the voltage equation, yeah, which describe the electrical port, and I will write either the swing equation, according if the machine is rotating or rotary type machine, or I will use the Newton's second law, the summation of the force must equal the mass multiplied by the acceleration, if this one is a linear type machine. And after that, I need a link between the electrical port and the mechanical port. And in general, this is either the torque or the force. The torque in the rotary type machine and the force in the linear type machine. So simply the theory of the electromechanical conversion is to find an expression for the machine torque in terms of the electrical variable and the mechanical displacement. Let's say. So simply here I can write the theory of the electromechanical energy conversion is to find an expression for machine torque, and here I'm assuming that I'm having a rotary type machine in terms of machine electrical variables. Which actually the current and the displacement of the mechanical system and the displacement of the mechanical system. Good. So simply the theory of the electromechanical system is to find an expression for the torque or the force in terms of the machine, the electrical machine variable and the mechanical variables. So simply here, if I specify for linear type motion, which means that linear motor, and we have here rotation type motion. So for the linear type motion, we have force. So simply here, I will say that the force must be written as a function of the machine electrical variables, which is the current, and the mechanical displacement, which is the x. While for the rotation type machine, here we have the torque must be written as a function of the same thing, the machine electrical variable, which is the current, and the displacement of the mechanical system, which is the angular displacement theta. Understood? Yeah. So simply.
طب دكتور الاكس شو هي؟
The displacement, the linear displacement. So simply here, if I'm assuming that this is the mover and this is the stator, and here let's assume that we have slots for the windings. Yep. Now, if I'm assuming that this is the reference point, from here I will measure the x. This would be the displacement. Yeah. So x is the linear displacement. While in the rotation time machine, in general, before that, this one we call it mover. Huh? This one in general, we call it mover. And this one in general, we call it stator because this part is stationary. Now in the rotating time machine, in general, we have stator. and we have rotor. The displacement in between, this one is called the gap. This one is the gap. The same thing, displacement here is called the gap. And this is very important. Without the gap, the machine cannot rotate. We need a gap in order to make a free motion for the machine. Now, this will be the stator, which is the stationary part of the machine, hold windings, distributed windings, let's say. And here we have the mover, or in the rotation time machine, or in the rotary time machine, we call it the rotor. This one is called the rotor. So in the rotation time machine, we have stator and rotor. In the linear time machine, we have the stator and the mover. So this is the shaft. Let's assume that this is the shaft here, where we can connect the mechanical system, and simply this will be theta, according to, let's assume this is my reference, and this will be theta. And theta here is the angular displacement. Do you have any question until here?
دكتور الموفر هو اللي بيتحكم يعني بالنمبر of windings.
No, the mover is the moving part, the part that's under motion. This is the mover. The stator is the stationary part.
Yeah? Now the linear type, it's the transformer, right?
No. The linear type motion, this can be electric train, by the way, is a linear motion or linear motor, the train. The relay, do you know the relay?
Oh, yes.
Yeah, the relay simply here, if I'm plotting a simple circuit, let's assume this is a core, and now I'm having here a coil, and if I'm injecting a current, let's assume in this direction, according to the right-hand rule, it will generate a flux, yeah, and the flux will be in this direction. Yeah. Now, if here I'm having a mover, let's assume a simple mover, and this is a meter. Now, if the flux across the mover, let's say, let's assume the flux across the mover, in this case, it will generate here what? EMF, and because this one is a meter, the current will be the current, let's say, will flow in the meter, and this also will generate what? A flux. Now, the flux between the two, either the force will extract or attract, let's say, attract the metal. So the metal can either move in this direction or in the opposite direction, according to the direction of the electromotive force. So in this case, this is the stationary part, and this is the mover, we call it. Mover, yeah? But in the rotation type, the rotor is rotating, it will spin in a same axis. Huh? Here the gap is changing, correct? According to this distance. If the metal is moving toward this direction, then the gap will be reduced. Yeah. If the metal is going in the opposite direction, the gap will increase. Here, the gap all the time, according to this plot, is uniform, because here I'm assuming cylindrical, let's say, cylindrical rotor. This is called cylindrical type machine. Also, I'm having another type of the machine in which the rotor is non-uniform. Something like that. And this one we call the salient machine. If you notice here, the gap is changing according to the direction or the angle of the rotor. Here the gap, the width of the gap here is larger than the face of the pole here. Now, if the rotor is rotating, let's assume I'm capturing another moment here. Here. Now, the place where the gap was narrow now become wider, and the opposite is here. So simply this means that this type of the machine is called salient type machine, and here the gap is not uniform. Here the gap is not uniform, while in the cylindrical type machine the gap is uniform. Later on I will discuss it with you. Okay. Until here, do you have any question? No? Okay. If you don't have any question, let's analyze a simple magnetically coupled circuit. Let's assume that we have a ferromagnetic core. And we have two windings placed in this core. So let's assume this is the first winding. And let's energize this winding by a voltage V1. So a current will flow, which is I1. Let's assume the number of the winding, or the effective number of the turns. Later on, I will tell you why I'm using the term effective number of turns instead of the actual number of turns. And in the here also we have another coil. The same thing, let's assume this is the polarity for the V2 plus minus V2. And let's assume that a current will flow here. This is I2 and this is I1. And the effective number of the turns is N2. Now, according to the right-hand rule, you know the right-hand rule, simply put your finger in the direction of the current. Your thumb will be pointed toward the direction of the flux. So simply here, the current, if I'm using the let's so simply, if I'm using the right hand rule, so simply the flux will be generated in this direction. Linking the first coil and the second coil. This is called the magnetizing flux for the first coil. So I will call this one phi M1. But simply also I'm having what? I'm having a leakage flux, which is a flux only linking the coil N1 itself. And this one we call it phi leakage 1. The same thing for the coil number 2. If I'm applying the right hand rule, do you see my hand? Do you see my hand? This is the direction of current.
No, doctor, I can't see it very well.
Okay, just a minute. Now, can you see my hand? Okay.
Yeah.
So this is the direction of the current. Do you see the winding? So this the current is coming here and entering to the winding. Yeah. The current will flow. Yes. Enter to the winding. Yes. Do you see it? I'm plotting here. So this actually what I'm representing by my 4 fingers, yeah, and the thumb is directed or pointed toward what? The direction of the flux. So it will be in the same direction. It will be in the same direction. So this will be the flux, the magnetizing flux is due to a current flowing in coil number 2. So this one I will call it phi M2. In the same sense, part of the flux is only link the coil itself. And this one I will call it the leakage flux for coil number 2. And simply this is a magneticable circuit, a symbol, 2 coils. So this is what we call it a magnetically coupled circuit. Now, this is what we call the core. Now, in general, the core is manufactured from a ferromagnetic material with high permeability. So simply this is ferromagnetic material with high permeability. For example, like let's say iron, for example. Yeah. Now, who can tell me the rule or the objective of the core? Why I need the core, by the way? Who can ask? Or if anyone asks why I need a core? Simply I'm having 2 coils. I can place the coils in free space. Yeah. And simply this will form Magneticable circuit. But simply why I need a core? Anyone? Amani? Amina or Amina? Amina?
Doctor.
Why I need? Yeah. Why I need a core? Anyone?
دكتور يمكن في ريشيو عشان الفولتية أتحكم فيها أقلل أو أزيد إشي زي هيك.
The core has no relation with the voltage.
دكتور ممكن سبب عشان تثبيت التو كويلز.
Now this is one of the objective that I need the core in order to mount the windings, correct? In order to place the winding and the core. But simply this is not the main, let's say, function of the core. Simply without a core. Yes.
ممكن عشان يصير في عندي induced voltage، يعني عشان يمشي فيهم الفلكس مش هيمشي بالهواء.
Let's say in order to direct and concentrate the flux. In order to direct and concentrate the flux, I need a core. Do you see? Without the core, the flux will go, let's say, away from the coil. With the core, the flux is guided and concentrated, by the way, and concentrated. So simply, let's say if I need to represent the Magneticable circuit, I can now represent it by a two coil elegant to each other. The meaning that the flux of the first coil, if I'm assuming this is the direction, and the flux of the second coil are elegant to each other. So simply, this is the flux of the first coil and the second coil. And of course, here I'm having a leakage of flux, which is only contributing with the current flowing in the same winding. Yeah. So I need a core in order to concentrate and direct the magnetic flux, and of course, in order to hold and maintain the winding. Now, the flux produced by a coil is equal to two fluxes, correct? Here, if you notice that, when a current flowing through the first coil, it will generate two flux. Yeah, one is the leakage flux, and the second one is the magnetizing flux. So simply, here we can write that the flux produced by each coil, of course, current in the coil, is equal the leakage flux and plus the magnetizing flux. So the first one, this will be the flux leakage, and this will be the magnetizing flux. Yeah. Now, if I will write the flux linking each coil, which flux link coil 1 and which flux links, let's say, coil 2? Who can tell me? Who can tell me the flux linking each coil is equal to what? For example, phi 1, which is the flux linking coil number 1. Here, phi L1 is linking coil 1, yes or no?
Yes.
So here I will write phi L1 plus
الفاي M1.
phi M1 linking, yes, phi M1.
Plus phi M2.
Phi M2 is also linking the coil number 1. In the same scenario, I can write the flux linking coil number 2 is the leakage flux plus phi M1 plus phi M2, correct? Now,
طيب دكتور M1 كيف بيرتبط مع phi 2؟
Now, do you see phi M1? What's the meaning of the leakage flux and what's the meaning of the magnetizing flux? The leakage flux is the flux that produced by a current in a coil and only linking the coil itself, which is true for phi L1. Phi L1 is only linking what? Coil number 1, correct? Phi L1 is produced by which current? I1.
I1.
Yes?
صحيح.
And it's only link what? Coil number 1. Now let's go in the second coil. Here what I'm having. The second current flowing in the second coil generate two fluxes. One is phi M linking the two coils. And the second one is the leakage flux, which only link its own coil. Yeah?
تمام.
So this is the definition of what? Of the leakage flux. So the leakage flux produced by a current flowing in a coil and links only the coil itself. But the magnetizing current is produced by a coil, or let's say produced by a current flowing in a coil and links all the turns of the coils. So here, phi M1 is generated by a current flowing in the coil number 1, but it's also links what? Coil number 1 and coil number 2, correct? The same thing for phi M2. The magnetizing flux is due to the current, the second current flowing in the second coil. The second coil produce phi M2 and phi M2 is linking coil number 1 and coil number 2. Yes? So here, if I'm taking this one, then here I'm having what? Two fluxes, two magnetizing fluxes. One is due to the first current and the second due to the second current. And I'm having here what? The leakage flux. So that's why the flux linking each coil is the leakage flux plus the magnetizing flux. So let's define the leakage flux and the magnetizing flux. So here I will try to put it in general form. So I will say that phi Li, where I is a counter, can be 1 or 2 or 3 according to number of coils. By the way, it's this analysis is not restricted to 2 coils. It can also generalize to a multi-coil system. So phi Li is the leakage flux produced by a current flowing in coil I and links only coil I turns. The same thing here. I can write for the phi Mi as the magnetizing flux produced by the current flowing in coil I and links all the turns of coil I1 and 2. or let's say, and links all the turns of the coils. And here, because I'm having 2 coils, so I will say coil 1 and coil 2. And 2. Yes. Good. So simply this is the what we call the leakage flux and the magnetizing flux. Now, sometimes it's impossible to link all the actual number of the turns. That's why in general we'll define in I, and I can be here 1 or 2 according to the number of coils I'm having. This one is the effective number of the turns of the coil I. So is the equivalent number of turns of coil, let's say I. So in I is not the actual number of turns, is the equivalent number of turns of coil I. Good. Now, if I need to write the voltage equation for the Magneticable circuit, now for this system, I need to write the voltage equation. So simply, the voltage equation is equal to what? If I'm writing here the voltage equation. The voltage equation is what here? Simply here I'm having input voltage, and any coil should, let's say, has some resistance, yes? You know that any conductor carrying current, there is a heat generated due to the resistance of that wire. So simply here I'm having what? I'm having a resistive, or let's say equivalent resistance. And simply this is what? This is actually inductive system, yeah? Yeah, this one is inductive system. And if I need to write the voltage equation, then I will go to use the Ohm law and the Faraday law of induction. So simply here I will say that in general I can write the voltage equation as V is equal IR plus d lambda by dt, where this one is the Ohm law and this one is the Faraday law of induction. Yeah. So let's repeat this one here, or let's start a new page. So if I need to write the voltage equation, and this is valid whatever the system that I'm analyzing, is a transformer or electric machine. In general, I need to write the voltage equation, which simply decomposed of 2 parts. One is IR plus d by dt of lambda. And as we said before, this is actually the Ohm law. And this is actually due to the Faraday law of induction. So if I need to finish my model, I need to specify lambda. And because here I'm having two coils, I will define a vector V, which equal V1, V2. So the current I will equal also I1, I2. The flux linkage lambda is also vector lambda 1, lambda 2. And R, if I'm assuming I'm having two coils, so R will be what? A diagonal matrix, consists of R1, R2. The self-resistance of the first coil and the resistance of the second coil. So if I need to expand, the voltage equation can be written as V1 is equal R1 I1 plus d by dt of lambda 1, and V2 is equal R2 I2 plus d by dt of lambda 2. Now, in order to finish the voltage equation, I need to define lambda 1 and lambda 2. And lambda is called the flux linkage. So lambda, the flux linkage. So lambda in general is equal N multiplied by the flux phi. So simply here, lambda 1 is equal N1 phi 1, and lambda 2 is equal N2 phi 2, and the unit for the flux linkage is volt second. Good. Now, the flux. If I need to find the flux is equal to what? According to the theory of electromagnetic and the equivalency between the electrical circuit and the magnetic circuit, the flux is equal the magnetic motive force over the reluctance, where this one is actually called the reluctance. So simply, the MMF, according to the Ampere law, is equal in I over the reluctance. So now, if I need to find the leakage inductance for the first coil, or coil number I, let's say in general form, this will equal to what? Phi Li will equal in I over the reluctance of what? Of the leakage path, Li. Correct? Yeah. Now, if I need to find the magnetizing flux, phi Mi, this is equal to what?
Ni في I
Yeah.
على الR reluctance اللي هي M magnetizing I.
So the magnetizing path. Huh? So if you notice here, if I return back here, whether I'm discussing the first phi M or the second one, the magnetizing path is the same, correct? Yeah?
Yes, yes.
The magnetizing path is the same. So now let's define in general the reluctance. This one is called the reluctance of the magnetic path. So this will be the reluctance of the leakage path, and Rm is the reluctance of the magnetizing path. Now, in general, the reluctance has a relation with the geometry of the material.
Reluctance depend on the time?
According to the geometry, if the geometry changing or no. For example, if we discussing a cylindrical type rotor, cylindrical, so whatever the rotor is moving, the gap is changing or fixed?
لا, fixed.
So in this case, the magnetizing path is fixed, yes?
Yes.
The same thing for the transformer. For the transformer, because here I don't have a mover. All the circuits are stationary. Here, the magnetizing path is changing or fixed?
لا, fixed.
Fixed. Now, in this case, the magnetizing path will be fixed. But if I'm discussing the following example, let's say. Now, the rotor having the following shape. Now, while the rotor is rotating, this gap will change or will be the same?
لا, change راح تكون, صح?
It will change. So in this case, the magnetizing path will change, because if I go from here and return back to here, it will different than if I'm going in this direction, correct? Yeah?
Yes. Yes.
Because you know that here what I'm having, iron, then I will have here what? Gap, then iron. And you know that the iron has high permeability, so there's no drop or let's say loss in the magnetic field on the iron. All the flux will be concentrated where, or the drop of the flux will be on the gap. Yeah. So simply, yes, the distance here is changing. So simply this means that the magnetizing path is changing. This is an example for changing of the magnetizing path. The same thing here. If this one has the following shape, let's say. And let's assume here I'm having a coil. Now, this is a mover. And according to the magnet, or the magnetic field, the mover can move up or down according to the direction of the force. In this case, the magnetizing path is changing. Why? Because the gap is changing. Yeah? But in the transformer here, the magnetizing path is what? Is constant. In the, yeah, in what we call it the Magneticable circuit in the stationary circuit. Yeah? Good. Now, in general, we know that the reluctance has a relation with the geometry and the type of the material. Huh? So in general, here I can write that the reluctance is equal the length of the material over mu multiplied by the cross section or cross area. There. So L is the equivalent length of the magnetic path. So simply here I can define L as the equivalent length of the magnetic path A is the cross-section area. And mu is the permeability. So here mu is the permeability. Now you know that the permeability of the free space mu 0 equal to what? In general, you know that mu 0 is equal 4 pi multiplied by 10 to the power minus 7 Henry per meter. And the permeability of the material is equal the relative permeability multiplied by the permeability of the free space. So the of a material mu is equal mu r multiplied by mu 0, and mu r, this one we call it the relative permeability. So this one is the relative permeability. Good. Any question until here? Any question until here? No. Okay. So let's write the flux in terms of the current and the reluctance. So phi 1, which was equal to phi L1 plus phi M1 plus phi M2 will equal. The first one is equal N1 I1 over the reluctance of L1 plus phi M1 is equal N1 I1 over Rm plus the second magnetizing flux is equal I2 into over Rm. The same thing here. The same thing here for the phi 2, which equal phi L2 plus phi M1 plus phi M2, and this will equal to the leakage is into I2 over the leakage magnetizing path RL2 plus the one is the same thing here, N1 I1 over Rm, and phi M2 is equal into I2 over Rm. Yeah. Now, if I multiply the first one by N1, and the second flux by N2, we will get what? Lambda 1 and lambda 2, the flux linkage. So simply here, we will have lambda 1, which will equal N1 square I1 over RL1 plus N1 square I1 over Rm plus N1 into I2 over Rm. The same thing for lambda 2, which will equal into square I2 over RL2 plus into N1 I1 over Rm plus into square I2 over Rm. Yeah. Now let's collect the terms. So collecting the terms, what we'll have? We'll have lambda 1 will equal N1 square over RL1 plus N1 square over Rm, all multiplied by I1 plus N1 into over Rm multiplied by I2. Who can help me with the second one? Lambda 2 equal to what? Who can help me with that?
N2 square.
N2 square
Over reluctance L2 plus N2 square over reluctance Rm. Magnetizing.
Yeah, I'm collecting the terms due to the second current, yeah?
Yes, exactly. Multiplied by I2.
Multiplied by I2 plus N1 into
N2 over
Rm
Rm multiplied by L1.
Yeah. Yes. Now, this is what? And this is what? You know that here I'm assuming a linear magnetic circuit. In linear magnetic circuit, this means that lambda can be written as L multiplied by I. This is by the assumption I'm assuming a linear magnetic circuit, which means that I'm neglecting the hysteresis and the eddy current, let's say, the hysteresis losses and the eddy current losses. Of course, we have a technique in order to suppress the hysteresis losses and the eddy current losses. For example, if I need to reduce the effect of the hysteresis, I will use a material with high permeability. And if I need to reduce the effect of the eddy current, I will, instead of making the core as a solid, one piece core, we can slice or eliminate the coil with multi pieces. In this case, the eddy current will be reduced. So in general, without loss of generality, we will assume a linear magnetic circuit in which saturation, the hysteresis effect, and the eddy current is neglected. So if this is the case, lambda can be written as L, and L is called the inductance matrix. The inductance. And this is the current. So this inductance is what?
Self-inductance.
The self-inductance. Why we call it self-inductance?
Because it depends on the first coil.
Yeah, it has a relation with what? With the first current flowing in the first coil. Yeah. And what about the second term?
The mutual.
Mutual inductance.
Mutual inductance. So simply, if the system is linear, I can use something called superposition, correct? I can kill I2 and say the flux that I'm having is due to what? To the I1. And if I calculate the value here, this will be the self-inductance. Yeah. So this actually what we call the self-inductance. and this is what we call the mutual inductance. Yeah. So in general, I can write lambda 1 is equal L11 I1 plus L12 I2, and lambda 2 is equal L22 I2 plus L21 I1. Now, what the relation between L12 and L21?
Equality.
Yeah, they are the same. So simply I can say that L12 is equal L21. Okay.
Yes.
So simply L11 will equal N1 square over RL1 plus N1 square Rm, and this is decomposed with L1, the leakage inductance, plus Lm1, which is the magnetizing inductance. So here the same, I can say that this is the leakage inductance, and this is the magnetizing inductance. And the same thing, I can write the L22, which will equal the N2 square over the RL2 plus N2 square over the Rm, which is the LL2 plus Lm2. Now, what the relation, or can I write Lm1 in terms of Lm2? We know that this one is equal to N1 square Rm, and this one is the Lm2. So simply I can say that from here, I can say that Lm1 is equal to N1 over N2 squared Lm2. Yeah. The same thing, the L12, which equals the L21, which equal N1 into over Rm, can be written in terms of Lm1 by multiplying for N1 over N2 Lm1, or N1 over N2 the Lm2. So simply I can also represent the L12 in terms of Lm1 or Lm2. This is multiplied by. No. So to this end, we can write the flux linkage L as lambda equal Li, where L equal L1 plus LM1. Here I can use N2 over N1 LM1. Here also I can use N1 over N2 LM1, and here L2 plus LM2. So now if I'm having the flux linkage, I can put it to the voltage equation and I can find the
طيب دكتور
mathematical model which represents the system. Yeah.
صح حكيت لنا L12 تساوي L21 ليش هون
Yeah.
إذا حب الماتريكس غيرتها؟
I'm not changing anything. It's the same.
طيب لازم N2 على N1 في LM1.
Now this one equal to this one. Yes or no?
يس بس بالماتريكس غيرتهم.
فمتخبط ب LM1 نكررها مرتين.
This is my mistake. Thank you. This is the LM2. Yeah. This is the LM2. Good. Okay. So this is my mistake. It was a typo error. So now if I'm substituting the flux linkage into the voltage equation, I can find the mathematical model for the Magneticable circuit. So now let's see. The voltage equation in machine variables. As which was the voltage equal Ri plus d by dt. Now instead of lambda, I can put Li. Yeah. Now see, here the inductance matrix is a function. Here the inductance matrix is a function of geometry only. Yes. Here the inductance matrix is a function of geometry, which means that it has no relation with the time. Yeah, it's only a function of geometry. So simply L is constant. Yeah. So here this inductance matrix is constant, which is a function of geometry. Yeah. Yes. Good.
Yes.
Good. So now, if I need to plot the equivalent circuit of the two Magneticable system, by equivalent circuit, I mean that I need to make a connection between the second coil and the first coil, electrical connection. And in general, you know that there's no electrical connection; they are magnetically connection. So simply, I need to highlight the equivalent circuit and the meaning of referring one current from one port to another port. So let's discuss with you the T equivalent circuit of the two magnetically coupled coils. And I will rewrite lambda 1 in terms of LL1 I1 plus LM1 I1 plus N2 over N1 I2 and lambda 2 LL2 I2 plus LM1 I2 plus N1 over N2 I1. Now, the meaning of the referring, if I'm assuming that this one here, this actually what? I2 is a current flowing in where? In the second coil, yeah? And affecting what? Affecting the first coil, yes? I2 is a current flowing in the second coil and linking all the coils. So in this equation, it will affect what? Lambda 1. So now, instead of N2 over N1 multiplied by I2, I can assume that I'm having I2 dash, which is the second current referred to the first current, in the sense that if I'm having this current, if I'm injecting this current I2 dash in the first coil, I will get the same effect as I'm injecting I2 in the second coil. And this is what we call it what? The referring. So here, let's assume let I2 dash equal N2 over N1 I2. So I2 dash, this current when flowing through coil number 1 produces the same magnet motive force MMF as the actual current which is the I2 flowing in the coil number 2. So this actually, we are referring I2 to coil number 1. So coil number 1 becomes the reference. So this is actually what we call referring. I2 to coil 1 in the sense that coil number 1 is the reference. Good. Now, if I'm changing the coordinate here, simply I'm changing the coordinate. Yeah? I'm assuming that I'm having a current and I'm injecting this current in the first circuit, and I'm getting the same effect as if I'm injecting the actual current in the actual circuit. So simply this can be seen as a change of coordinate. But you know that if I'm changing the coordinate, the power should not be changed. Otherwise, I'm discussing another system, or otherwise I'm changing the system. So simply this means that the power must be what? Must be preserved or must be the same. So here I can write for you that power is to be unchanged by the change of the variable. So if I'm writing here the apparent power, V2 I2 this must equal V2 dash I2 dash. Yeah. Now, I2 dash is equal to what? According to our assumption, I2 dash was equal to what? I2 dash equal to what?
N2 over N1 multiplied by I2.
Yeah. So it will equal N2 over N1 multiplied by I2. So simply this means that V2 dash in terms of V2 must equal to what? N1 over N2. Yeah. So simply now N1 will cancel N1, N2 will cancel N2, and the power is not changing under the change of the variable. If the power is changing under the changing of the variables, know that you are changing your problem and it's not correct. So simply from here, we can conclude that V2 dash is equal N1 over N2 multiplied by V2. And because the flux linkage is following the voltage, this means that I2 dash is equal N1 over N2 multiplied by lambda 2. Yeah. So now if I need to write the flux linkage referred to the first coil, then lambda 1 is equal L1 I1 plus L M1 I1 plus I2, and this one we achieved it I2 dash by the change of the variable. Remember that I2 dash is equal to what? N2 over N1 I2, and I2 dash is what? A virtual current that I'm assuming that I'm injecting to the first coil in order to achieve the same effect as if I'm injecting the actual current in the second coil. So here I don't need to do anything, but I need to refer the second equation to the first coil, which is lambda 2, which equal to L2 I2 plus L M2 N1 over N2 I1 plus I2. Now, if I need to refer the flux, I will multiply by what? If I need to have lambda 2 dash, I will multiply by N1 over N2. So here I will multiply both sides by N1 over N2. Automatically here I will get lambda 2 dash will equal N1 over N2. Now I2 dash, I2 in terms of the I2 dash is equal to what? Remember, I2 dash was equal N2 over N1 I2. So simply I can write I2 equal to what? N1 over N2 I2 dash. Now I need to represent the second equation in terms of what? Of the variable that's related to what? To the first coil, which is I1 and I2 dash. Those are the variable referred to the first coil. So simply here I will put N1 over N2 I2 dash plus N1 over N2 due to the multiplication. Yeah, this is I1. So simply here I don't need to change anything. This will be N1 over N2 I1 plus this is I2 dash. Instead of I2 dash, I will put what? I will put N1 over N2 I2 dash. Now, the second flux linkage is written in terms of the parameters of the first coil, which is the I1 and the I2 dash. So if I'm collecting the terms, I think here I'm missing this one. Huh? This would be the L2. Yeah. So so now I can write lambda 2 dash equal to, and this one, if scalar, I can say it will be N1 over N2 squared multiplied by L2 I2 dash plus, and I think here I'm missing the LM2. Huh? Here I'm having LM2. Yeah. And here also, if I'm N1 over N2 as a common factor, I will get also N1 over N2 squared LM2 multiplied by I1 plus I2 dash. So now I can write lambda 2 dash as LL2 dash plus multiplied by I2 dash plus LM2 dash multiplied by I1 plus I2 dash, in which this will be the referred, let's say, leakage inductance, and this is the referred mutual inductance.
Doctor, refer to one?
Yeah, refer to one. I'm referring to the first coil. Okay. Now, if I need to plot the T equivalent circuit, then I will have two ports. This is the first port, which is the V1 plus minus V1. And for the V1, I'm having the resistance, which is the R1. Then I'm having the leakage inductance L1. And I'm having the magnetizing inductance, which is the LM. Yeah. And the same here. I'm having plus minus now, V2 dash. And here I will have the R2 dash. And here I'm having the L2 dash. And here a current will flow. I1, and here a current will flow, which is the I2 dash. Yeah. Now the R2 dash, actually, if I go to the V2, which was equal R2 I2 plus d by dt of lambda 2. If I multiply here by the N1 over N2, N1 over N2, now this one will be N1 over N2 R2, and for I2 I will use N1 over N2 multiplied by I2 dash. So simply this is actually the the R2 dash. This is actually the R2 dash. Now, this is what we call the T equivalent circuit. This is what we call the T equivalent circuit, as coil 1 is selected as a reference. So this is actually the T. Okay. Of course, I can use coil number 2 as a reference. In this case, I will refer the coil number 1 to coil number 2. I can do it also with the same procedure. It will be the same. And of course, this method can be used for any number of coils wounded on the same, let's say, core. It's not restricted to be only 2 coils. It can be 3, 4, or more. The same principle is applicable. Now, let's give the following example, let's say. Find all parameters in the T equivalent circuit given the following. When coil number 2 is open circuit, the applied voltage to coil number 1 is 110 volt RMS value, 60 Hertz. The current was 1 ampere and the input power was 12 watt, and the input power was 12 watt. The second thing, when coil number 2 is shorted, the current flowing in coil number 1 is 1 ampere when the applied voltage is 30 volts, 60 Hertz. The power during this test or this condition is 22 watt. The power during this condition is 22 watts. assume L1 equal L2 dash with coil number 1 is selected as a reference. With coil number 1 is selected as a reference. Okay, think about this one, and I need to make a call. Huh? Think about this one for 2 minutes. How I can find all the parameters in the T equivalent circuit? يسرى.
دكتور
How I can find the parameters?
من قانون الباور بدي أبلش فيه.
قانون الباور. طيب قانون الباور. So
أنا معي الماجنتيود للفولتج.
magnitude of voltage. Okay, so P1 is equal V1 I1 sine theta. Okay. So now the first test, this one we called what? This is called what? Open circuit test. Huh?
دكتور بنحكي 12 على 1.
Yeah.
نطلع الباور فاكتور.
Okay, so simply from here I can find the power factor, which is the cosine theta, which will equal P1 over V1 I1. Okay, so from here I can find theta, which is what? Cosine inverse of P1 over V1 I1. So this will equal cosine inverse of the power was 12 over 110 multiplied by 1, and if I do the math it will equal 83.7 degree. Lagging or leading? Lagging. Why lagging?
لأنها positive.
Has no relation. Here
لا inductance صح لأنه inductance.
Yeah, because we have inductive, this inductive circuit. Inductive circuit. And do you know the meaning of the inductive circuit? The current lag the voltage. Huh? So if this is the voltage, so this will be what? The current and this will be the theta. So simply here, the current lag the voltage. You know the meaning of the lagging and leading, huh? Yes? Okay. So I can find the impedance, yeah? The impedance, Z1. Of course, the first one we call it what? The open circuit test. So only we have what? We have the R1, we have here the L1, and here we have the LM. So if I can find Z here, which will equal the V1 over I1, I can find the impedance, yeah, and the impedance is decomposed as real part and the imaginary part. The real part will be the R1, and the imaginary part will be what? The total X here, huh? Which is the omega multiplied by L1 plus omega multiplied by Lm. So now let's find the impedance here. And of course, this is valid if I'm neglecting the hysteresis or the core losses, which means that I'm assuming a linear magnetic circuit. So Z will equal V1 over I1, and I'm considering V1 as a reference, 110 with angle 0 over the current now is 1 with angle what? Minus 83.7 degree. Why minus? Lagging inductive load or inductive circuit, let's say. So this will be 110 with angle 83.7 degree. This is what we call it the polar form. If we transform it into rectangular form, it will have a real part and the imaginary part. So it will be 110 cosine 83.7 degree plus 110 J here sine the 83.7 degree. And if we do the math, this will equal 12 plus J109.3 ohm. Now this actually the R1, yeah, and this actually is what? This will be the XL1 plus the XM, yeah, and this will equal 109.3 ohm, yeah. Now, until now, we found what? The first coil resistance and the combination between the XL1 and the XM. From the second test is what? The coil 2 is shorted. This is called
short circuit
test. Okay, this is the short circuit test. Now, if I'm plotting the circuit under the short circuit test, then I will have here the R1, the L1, and here Lm, and here I will have the R2 dash, and here I will have L2 dash. And now here I'm imposing voltage V1, which I think it was 30 volt, and the current here will flow, and the current here was 1 ampere, I think. And during this test, the power was 22 watt. Now, in general, in the transformer, when we design the transformer, we design transformers such that the XM is much larger than, as a magnitude, than the R2 dash plus JXL2 dash. So simply those two impedance are in parallel, and if I'm calculating the parallel XM with the R2 dash plus JXL2 dash, simply this almost will equal R2 dash plus JXL2 dash, under the assumption that I'm I'm considering transformer, and in general the transformer is designed such that the magnetizing inductance is much larger than the other impedance in the system. If this is the case, then simply the circuit will be simplified to the following. Here I'm having R1, we know the value, LL1, LL2 dash, and here I'm having R2 dash. Now the same thing, I need to find the impedance. So I need to find the impedance Z, which equal V over I. Yeah, and simply Z will equal, the voltage was 30, I think, with angle 0, and the current was 1 with angle. I need to find the angle of the current, so theta, the same thing, is equal cosine inverse of the power P over VI. So here it will be cosine inverse. The power in this case is 22 over the voltage is 30 multiplied by 1, the current, and in this case will be 42.8 lagging, of course. So here I will write minus 42.8. Now if I do the math, I will find this one will equal 22 plus J 20.4 ohm. Now R total is equal 22, which equal R1 plus R2 dash. So simply I can find R2 dash, which equal 22 minus R1, and I think 22 minus 12. So in this case, it will be 10 ohm. This is the same thing. I can find the L dash. Yeah. Now in this case here, the X total is equal to 20.4, and this will equal the XL1 plus XL2 dash. And because by assumption we assume that XL1 is equal to XL2 dash, so simply this means that L1, which will be LM1, LM1 or LL1, sorry. So LL1, which will equal LL2 dash, will equal to 10.2 over omega, and omega is 2 pi f. Yeah, so this will be the 10.2 over 2 multiplied by pi multiplied by 60 hertz. So I can calculate it. Yeah, if I calculate, this will equal to 27.1 millihenry. Now if we return back to the first part, this one was equal XL1 plus XM. So from here I can calculate the XM. So XM will equal 109.3 minus XL1, and this will equal 99.1 ohm. So I can also find LM, which will equal XM over omega, and this will equal to 262.9 millihenry. So simply from the open circuit test and from the short circuit test, we can specify all the parameters in the T equivalent circuit. Do you have any question?
دكتور بس الأم دائما بشيلها.
Now here under the assumption that XM, which equal to what XM? XM is equal omega LM. Now this impedance and this impedance in parallel. Yeah, and you know that if I'm connecting two impedance in parallel, then the resultant impedance will be what? Smaller than the smallest value in the combination. Huh? And if one is very high, then the equivalent resistance will, or the equivalent impedance will equal to what? The second impedance. And this is valid because here this is a transformer, and the transformer design says that the XM is much larger than the impedance, which is the R2 dash plus JXL2. So in this case, I can neglect the Lm. Otherwise, I need to give you the core losses in order to calculate.